One of the most important relationships in physics is the work-energy relationship. Work is defined to be the change in energy for an object. That is the energy added or removed from the object. We add or remove energy from an object by applying a force to it, and the work or change in energy is found by getting the product of the force and the distance traveled by the object while that force was applied. That force must be in the direction of motion or against the direction of motion. So we only look at the force that is parallel to the distance traveled. Okay, in this example, you'll notice that no work is being done. No energy is being added to this object so long as this object is at rest. In order for work to be done, this object must move through a certain distance. So if we allow the object to travel a certain distance, and we call that delta x, the energy added to the object is simply a product of the force we're applying and the distance that we move. So as you saw, the object, once it started to move, had energy, and the energy it had at any specific moment can be found from this work equation, force times delta x. Okay, once we do work to an object, that energy that we give it can take on many different forms. So in this example, we're going to have an astronaut in space who has a fire extinguisher with him. He will use the fire extinguisher to create a thrust. In this example, the thrust will be 115 newtons. So as we activate our fire extinguisher, we notice that our object starts gaining energy. When we shut off our fire extinguisher, our astronaut will still have that same amount of energy. In this case, it's energy due to motion. This is known as kinetic energy. So if we took the force that was applied to the astronaut, we multiply by the distance that he traveled. That will give us the energy that was added to the astronaut. That energy is energy of motion. It is known as kinetic energy, and we find it by taking 1/2 the mass of the object multiplied by the velocity that he has squared. Kinetic energy, energy of motion. We could also give an object what is known as potential energy due to gravity. In this case, we have a safe attached to a string, and the string is attached to a motor. When we activate the motor, we see that the safe is lifted at a slow and steady speed. Since the speed of the object is not increasing, we are not adding kinetic energy to this system. The only change in kinetic energy occurred at the very first moment. After that time, all energy added will be turning into potential energy due to gravity. The potential energy of this object will be determined by how far we have lifted it from its original location, the strength of the gravitational field, and the mass of the object. So when we stop our object from moving and we measure how high we have lifted it, and we multiply that by the mass of the object and the strength of the gravitational field, we will get the energy stored in this system. Were we to cut this rope and allow this thing to fall back to Earth, that potential energy gravity would turn into kinetic energy. Realize when we calculate this potential energy due to gravity, it is actually a relative value based on our initial starting location that we're measuring height from. So in this example, we're calling this level the 0 point for the potential energy gravity. So this is the energy it possesses relative to this 0 point. That formula for potential energy due to gravity is limited to situations where there is not a large change in the gravitational field as our object is moved from one location to another. In some instances, we need to develop a new formula for potential energy gravity. So for instance, in this example, when we move our object away from the larger object, there is going to be a large change in the gravitational field that the moving object experienced. Whenever that is the case, instead of using the formula we had for potential energy a few moments ago, we need a new version, which will be known as our universal gravitational energy. It's going to look a lot like the gravitational force formula, which should not be surprising since energy comes from forces. Okay, so the work done is force times distance. So our gravitational energy formula looks like this. Gravitational constant times the product of the masses divided by the distance between the objects. Notice it's not squared like it was with force. Just like with the other potential energy gravity formula, this is a relative formula. So in most instances, we'd want to use this formula twice. So if we take an object from a starting location and we move it to a new location, what we'd want to do is calculate the potential energy gravity it had in the first location, calculate the potential energy gravity it has in its second location, and subtract to find the change in the gravitational energy. This is the really important number because this tells us how much work we did to our object. If this object were to fall from location 2 back to location 1, this potential energy gravity would turn into kinetic energy. So again, knowing the value for the potential energy gravity at the 2 points by themselves is not as useful as the difference between the gravities at these 2 locations. The work that we do to an object can also be stored as potential energy elastic. So in this example, we're going to use a changing force to add energy to this spring. And as we stretch the spring, we're going to have that energy stored as elastic energy. The reason why it is a changing force this time is because the farther we stretch the spring, the greater force is required to stretch it a little farther. So it turns out that our energy stored in the spring will equal the average force that we applied to this system, which would be 1/2 of the maximum force times the distance that we stretched it. So the delta x will become squared. So in this example, we take our force probe, we pull on the spring, and we stretch it a certain amount. That stretch will allow us to figure out how much energy is stored in the spring. So again, the maximum force we had to apply was right now when it's at its greatest distance. That would be k delta x. The average force that we applied, since originally there was no stretch and there was no force needed, so our average force is 1/2 k delta x, and we stretched it by a distance of delta x. Okay, so that would be the energy stored in the spring. So to summarize, all energy comes from work. Work is the energy that we either add or remove from an object. We add or remove energy using forces, and work is the product of the force times the distance. The force must be in the direction of motion.